My name is David Gray and I work at 4th ISL, and I am a member of the ATO2nd Science and Technology Laboratory, and here we are at the headquarters of 4th in Heraklion, Crete, Greece. 4th is the largest research institute in Greece, established in 1983. The building in front of us is located in the campus of the Science and Technology Park of Crete. This hosts 4 of the 6 institutes of 4th, the Institute of Electronic Structure and Lasers, the Institute of Micromolecular Biology, and the Institute of Computer Science, and the Institute of Applied Mathematics. The ATO2nd Science and Technology Laboratory is one of the major laboratories of the Institute of Electronic Structure and Laser. The mission of the laboratory is to generate, characterize and use attosecond pulse trains and isolated attosecond pulses. These pulses are produced through nonlinear phenomena that are recurring when intense femtosecond laser pulses are interacting with gases. Here we have the oscillator of the laser, and this drives the whole system. So we start off with a CEP laser at a few megahertz and 7 femtoseconds. We take the beam and we boost the beam in the booster. This is like a preamplifier system, and it drops down the frequency from megahertz down to 10 hertz. And then we stretch the laser pulse from 7 femtoseconds to some picoseconds in the stretcher. And the stretcher part of the pulse goes into a regenerative amplifier. And then this does the first pass of amplification after the booster. From there we have a gain control to widen the spectrum of the laser to keep the spectrum wide. And from there we go through 2 sets of multipass. The first multipass goes up to 20 millijoules, and then the second one boosts it right up to 400 millijoules. After this we have to recompress the pulse in the compressor here. And this uses a grating to take all the spectral components of the spectral and compress them so they all arrive at the same time. And after this system we have to have everything in a vacuum. The entire system is located in a cleanroom environment connected with the rest of the laboratory through vacuum lines, as the large laser beam intensity does not permit propagation in the air. This is because the unfocused laser intensity of 10 to the 12 watts per centimeter squared is so high that it can induce nonlinear propagation in the air that would destroy the laser parameters. For this reason, propagation only in vacuum is mandatory when the full laser beam is used. A further characteristic of the system is the so-called pulse contrast, the ratio of the pulse height to the pedestal, including the pre-pulses. This contrast is 10 to the 12 and is an important characteristic for the laser surface plasma experiments, in particular the relativistic interaction range. The requirement for the generation of energetic attosecond pulses is not to deplete the generating medium, which here is a gas jet during the interaction with the laser pulse. The laser frequency is then converted either to a comb of harmonics of the laser frequency, the superposition of which forms an attosecond pulse train, or it is converted to a coherent XUV continuum that synthesizes an isolated attosecond pulse. The laboratory puts particular emphasis on the generation of energetic attosecond pulses. Talking about energetic pulses, we need to explain what is meant by this term. We call an attosecond pulse energetic when its parameters are such that when it is focused, it reaches so high intensity that they cause a nonlinear process. Several 2 XUV photon processes have been indeed reached so far. But why do we target 2 XUV photon processes? The reason is because they are an essential tool for the temporal characterization of pulses. The 2 photon processes are used routinely for the measurement of the duration of visible or IR femtosecond pulses. 2 XUV photon-based characterization of attosecond pulses is successfully performed in few attosecond laboratories because it requires high XUV pulse intensities. We have them, and we use them for the measurement of the attosecond pulse duration. A second reason for targeting 2 XUV photon processes is that they are the basis for XUV pump, XUV probe studies. the technique with which the intrinsic dynamics of an atom or molecule are measured. Indeed, in this laboratory we have been able to measure dynamics in atoms and molecules that occur in very short time interval of the order of 1 femtosecond, applying this technique. A requirement for the generation of energetic attosecond pulses is not to deplete the generating medium, which here is a gas jet during the interaction with the laser pulse. If the laser intensity is too high, then all the atoms or molecules of the medium will be ionized during the rising of the laser pulse and will never interact with the peak of the pulse. This is known as ionization saturation. This has a consequence that not all laser photons will be used in the frequency conversion process, and more than this, the produced electrons that reduce the generation of attosecond pulses because they destroy the so-called phase matching, a propagation parameter that is very important for an efficient generation of harmonics and thus attosecond pulses. With phase matching, it means the conditions under which XUV waves generated at different positions along the propagation are in phase. Both effects, ionization saturation and phase mismatch, substantially reduce the conversion efficiency. In order to circumvent this obstacle with substantial laser intensity that is available, we need to reduce the intensity such that it is below the ionization saturation intensity. This can be done by using long focal lengths when focusing the laser in the harmonic generating medium, which is called loose focusing geometry. Since the produced XUV radiation will then need some propagation distance in order to diverge to some useful cross-section, the entire length of the attosecond beamline is becoming several meters. The beamline is using focal lengths of 3 meters and a newer one which will be up to 10 meters long. In this beamline, this chamber hosts the laser focusing system. The generation occurs in a pulse gas jet in this chamber. The separation of the XUV from the laser beam is achieved through reflection of the XUV and absorption of the infrared by a silicon plate placed in this chamber. The XUV spectral range to be used in the experiment is selected using metal filters placed in this chamber. They transmit a certain spectral interval while absorbing the rest. Because the driving laser is a many-cycle laser, the generated attosecond pulses are emitted in the form of pulse trains. Each pulse of the train is generated every half cycle of the laser field. In order to generate isolated pulses instead of trains, a polarization gate method is used and the corresponding device is placed in this chamber at the beginning of the beamline. After having produced the pulses, we want to measure their duration and eventually use them. Both happens in the last chamber. The harmonics of the XUV continuum generated is strong enough to induce a 2 XUV photon ionization process in a second pulse gas jet, and the products of the ionization, either electrons or ions, are measured in the time of flight spectrometer that can operate either as an ion mass spectrometer or as an electron energy analyzer. For the pulse duration measurement, we are applying a technique known from femtosecond pulse metrology as second-order autocorrelation techniques, while dynamics are measured through XUV pump, XUV probe measurements. Both are 2 XUV probe processes that require high XUV intensities and thus tight focusing of the XUV radiation. The XUV is focused by a spherical gold mirror to a focal spot that has been measured to be of the order of 1 to 2 microns in diameter. This leads to XUV intensities up to 10 to the 14 watts per centimeter squared, by far high enough to induce measurable 2-photon ionization. Both the second-order autocorrelation and the XUV pump XUV probe technique are based on 2 identical pulses that are separated in time with a variable delay. Since only very specialized devices can be used as beam splitters in the XUV spectral range, and those have a very low energy throughput, we are using a wavefront divider instead. The focusing spherical mirror is cut into 2 equal parts, one of which can be moved with respect to the position of the other along the propagation with a few nanometer accuracy, using a piezoelectric translation stage. This introduces a variable delay between the 2 pulses formed by the wavefront divider and allows for the recording of the second-order autocorrelation trace and/or the pump probe trace, measuring the product yield of the interaction as a function of the delay. As you can see, the lab space is new. We moved into this laboratory a few months ago and we are still in the process of putting together the beamline and workstations. A second attosecond beamline based on the harmonic generation in gas media will be built along these tubes, which are the cooling water tubes of the beamline. It will be a longer one with a maximum focal length of the IR focusing mirror of 10 meters. In this beamline, we will be able to use the total laser energy without depletion of the gas target due to even looser focusing, and thus due to an increased area of the focus. With these parameters, we are expecting to reach XUV intensities 10 to the 16 watts per centimeter squared or higher, entering the strong XUV field range.